Так, once again, спасибо за приглашение, and I'm going to switch to English because I'm more used to talk about this subject in English. I would like to talk about a model that aims to describe how brain learns to orient in space based on what we know about physiological mechanisms of spatial orientation. Now, the current paradigm on the subject is that spatial cognition, any form of cognition, fundamentally emerges from neuronal activity, right? So neurons somehow collectively represent the external world and create an image of it in our minds. In particular, we believe that neurons create complex temporal codes that somehow translates into geometric aspects of reality as well. And I should say that not only the mechanisms, never mind the mechanisms, but even the principles of this translation are currently completely unknown and actually quite mysterious, and rightly so, because these phenomena are of fundamentally different nature. On the one hand, we have this ideal world of geometry, this platonic world of geometry. And on the other hand, what we have is basically highly complex Morse code. And how in the world this Morse code translates into geometric reality is, it's a very complicated question. Actually, it's nothing short of a miracle. And a big question is how to even connect the two ends of this question. Now, of course, what we know about this, all our approaches are coming from animal electrophysiology, because we fundamentally believe that principles of spatial cognition are the same, or at least similar, right? So the fundamental question that we would like to ask is, okay, how neurons encode spatial entities, spatial patterns, and spatial memories. But this way of asking question proves to be kind of open-ended and conceptually complicated. So we prefer to ask our questions somewhat differently, in a somewhat simplified manner, actually conceptually simplified manner that is easier to address experimentally. We basically ask how neurons respond to spatial entities. And later I'll talk about how these two ways of addressing the question are actually different, and difference is important. But the second way of asking question has turned into a key idea that underlies essentially the entire field. We believe that neurons respond to these firing domains, firing fields. The idea is that it's basically possible to identify a certain space. It can be physical space or auxiliary space. And the idea is that we can identify domains in that space, which we call firing fields, such that neurons respond, each neuron responds to a particular domain. So this is essentially our current dominating way of addressing that miracle question, how neuronal spiking connects to spatial entities in the format of response. And I should also say that whether we say it explicitly or not, we basically think of this as some kind of a mapping from, I should say, use this thing here, some mapping from cognitive space, cognitive representation, into representing space. So representing space is serving as some kind of a probing space for interpreting what is happening cognitively. And a simple example of this that everybody is familiar with are, of course, place cells. Each cell is active in a small region in navigated space. Together they form a map of locations. So in this case, representing space coincides with navigated space. And we're basically, when we're building place field map, we're essentially thinking about mapping cognitive representation of space into what we observe in navigational environment. Another example are head direction cells. Here, cells that become active when the animal's head is oriented in a particular direction, right? So the firing fields in this case are angular domains in the space of orientations over which cells become active. And the same story, we have, we're mapping neuronal activity into some kind of representing space, and this helps us to interpret what is happening cognitively. Another example, recently discovered bats, representing space for head direction cells in bats, which is two-dimensional torus, and more examples, grid cells and parietal cells and cells in visual cortex. Essentially, this is universal way that we use to interpret neural activity in essentially any brain area. Now, when we say that spiking activity represents a spatial map, what we essentially mean is that the animal, we presume that the animal has a stable representation of space, and maybe the space is somehow, internally split into domains, and then we essentially presume that this stable cognitive representations of space is manifested as a stable map of firing fields. So when the animal is moving in this field, that induces activity of neurons, and each neuron, being that this map is stable, represents a spatial domain. That's the philosophy, basically. And when similarly, when the animal is moving in the space, that induces a trajectory in the space of orientations, which is crossing fields, firing fields in the space of orientation. The same thing. Every time some kind of an agent, the animal itself, or its head, or its gaze, or some kind of representation of animal's activity is crossing this domains in the representing space, and that induces activity, which allows us to make this connection, spikes and spatial domains. And at this point, I'm going to build a schematic representation of the data. So I'm going to represent, active neurons by a vertex of graph or simplicial complex, and same thing for spatial domains are going to be vertices. Now, to slightly extend this context, when we talk about two neurons co-active, well, if each one represents a region, co-active neurons represent two overlapping regions, which I formally will describe as combination of as one-dimensional simplexes, these objects, two vertices in one sense or another sense, and so on. Like three neurons represent three overlapping regions, two-dimensional simplex, and so forth. Now, to demonstrate the power of this approach, it's a very simple demonstration of power of the approach. Imagine if we look at the animal that is moving in a simple environment. So what you are seeing here is kind of a top-down view on a circular environment, and this white spot is a moving rat. So imagine that I know place fields of so many cells. In this case, I have about 40 cells active in this environment, and some of them are becoming active at every moment. And I can carry a very simple computation. I can follow which cells are becoming active, right? And these active combinations of cells, what I said a few minutes ago, is that I think of them as of simplexes, right? So it's a series of activations of cells are simplexes. And if I know where the place fields are, and I can estimate how they overlap in space, and from that I can estimate the animal's trajectory. And you see, this white spot is the actual location of rat, and this is my estimate what the rat would be based on just 40 cells or so, very few cells. And you see that estimate is actually pretty accurate, which is to say that this kind of procedure provides us with very good idea. The cells know quite a lot about what is happening spatially, and this sequence of this series of simplexes that we generate, which seems to be like, it might appear as a schematic or kind of abstract representation of what is happening, and actually gives us a very nice representation of trajectory, but in this, this kind of topological language, in the language of simplexes. What's interesting, we can actually extend this approach to interpret what is happening when the animal is in quiescent state or in sleep. These replays of animal activity, we can interpret it in the same exact way. Basically look at coactive combinations of cells, and since if we know what place fields are involved and how they interact, we can actually interpret what is happening when the animal is producing this activity offline. So basically we're reading its mind. What is happening, of course, is a different time scale, about 10 times faster, but the same exact principle is applying, and we can decipher what is the meaning of replay activity when the animal is in sleep. So it's all wonderful. Just this is just to demonstrate that what is happening has something to do with reality. But I should say that a key part of this algorithm is that we start by knowing what are the place fields and where they are and so forth. But the brain itself, of course, doesn't necessarily have access to this kind of information. This information is external. It's something that we are using to to illustrate, to interpret our data. So if we would like to know how the brain works on its own, we have to get rid of this. This kind of information and interpret what is happening in internal terms. And we try to do that without reference to place fields. We don't have space, as we know it. we have instead, we have these combinations of coactive simplexes. We can still interpret it as simplexes. We can still build our simplicial paths, simplicial trajectories. Then we can, ask how these paths accumulate and what structure do they form, right? What turns out that they form basically a schematic map, a structure of topological nature, which is called simplicial complex. Basically, it's a agglomerate of these simplexes. It's a basic object of algebraic topology that was, many times discussed, and in this school also it was discussed many times. So we can evaluate its structure, and basically from that we can describe in internal terms what hippocampus in this case knows about animals' movements. Now, this structure is topological in the sense that the shape that I drew here is some shape, but this shape is completely conventional. It's arbitrary almost. It knows nothing about geometry of, what's what in here. It only knows about adjacency. So intuitive idea what this thing represents is pretty much like a subway map of a city. The city itself and the actual layout of subway lines in a city is, of course, it's a geometrical thing, of course, but the schema, the subway schema, is a topological object. So in that sense, you can think of simplicial complexes as multi-dimensional, subway map of, whatever cognitive map represents. It's an intuitive way of thinking about this. Now, yes. So another thing I am to say is that a specific property of these complexes that we build from spikes is that they are time dependent, right? So spikes unfold over time, and we're looking at how cells become coactive in time, and each coactivity is represented by a simplex that generates a time-dependent simplicial complex. And dynamics of this simplicial complex, which are now time-dependent, may serve as a model or as a metaphor for spatial learning process. And we can actually, with this in mind, we can carry very simple simulations. Imagine we allow the rat to run in a small environment. It can be simulated data or it can be the actual data. Look at these combinations of coactive cells shown here. Each combination corresponds to a simplex. We can assemble simplexes into simplicial complexes and follow that dynamics. And this is going to be our representation of learning process. So this is what it looks like. A quick slide on here we have basically following the way to describe the simplicial complex. We can describe, for example, how many pieces it has. And this diagram here shows these pieces. Each line corresponds to when a particular piece appeared and when it disappeared. So this appeared here and disappeared, disappeared. This one appeared and continues forever. And we also, on the other hand, can look at one-dimensional holes, two-dimensional cavities, and this diagram shows for one-dimensional holes, same thing, when they appear and when they disappear. Now, since I know where my animal is running, I know how many pieces that environment has and how many holes it has, I know what to expect from this diagram. I would expect that cognitive representation of space should be the same as the actual physical space. I would expect to have one piece and one hole in this specific case, and I can estimate the time that it takes. And usually, we get some value. And we never insist on the actual number, something around 4 minutes. What's important is the time scale. A few minutes, 2, 3, 4, 5 minutes, depending on the size and complexity of your environment. Now, same thing can be done with head direction cells. Because as I said, when an animal is moving in the environment, it's inducing changes in orientation, which is basically trajectory in this representing space here. And that induces another simplicial complex, which we can think of these simplicial complexes as discretizations of our representing spaces. So this complex is, basically discretized representation of this space, and the complex I showed before is a discretized representation of navigational space. So this is how it works. Again, for head direction cells, also I can estimate how long it takes to find out that, directions are living in one-dimensional topological cycle. Wonderful. And we get something like, 1 minute, 1.5 minutes, simple estimate that allows us to know, the space occupied by directions. But now with these instruments in mind, we can actually ask a more intelligent, biologically more relevant question. basically, given that we have a network that knows about locations, and that's hippocampus, and a network that knows about directions, we can ask question biologically more relevant, actually, what, might this kind of information, these instruments be enough to learn how to orient in space? Basically, if you know places, directions, you can ask yourself, do you know enough to guide yourself, from place to place along a particular direction, right? So the question is how to interpret orientation task. And I should say that I'm talking about interpretation because it's not so obvious what does it mean exactly, learn to orient in space. Now, broadly speaking, in general terms, I would say that learning to orient is, learning directions at every location, something like this. Okay, now what does it mean exactly? Now, first of all, locations, we already mentioned, these are unique combinations of coactive place cells, or in a safer way to say it is to say that unique combinations represent individual locations in the map. So if you think of this as my place fields and these are locations, so each location corresponds to a particular combinations which are simplexes, right? So each location corresponds to a simplex. And when we have a physical path that goes through locations in some sequence like this, for example, right, it just moves from point to point. At the same time, representation of this is a sequence of simplexes going through this coactivity complex. And it's precisely the same thing I showed before, the simplexes running when I was showing these movies about moving rat. Now, at this point, I would like to make a connection with what I said before about topological learning, because previously I said that, spatial learning, we view the spatial learning as a process by which cognitive map acquires its topological shape, right? But now, from the point of view of path integration, we learn, path navigation. We learn topology of cognitive map over here for what purpose? Because we essentially want to know what obstacles these paths can run into, right? Because once I know the obstacle, if, for example, if I have a small environment like this, and I have, path 1 and path 2, I would like to know, like, how different these paths are, or maybe are they the same in qualitative sense, or are they different? And the answer to this is basically in terms of how many obstacles I have, how many pieces I might have in my space. So when I'm computing topology of my space, I'm essentially trying to classify paths. It's, a possible perspective of what I'm doing, right? So the answer, what does it mean to learn to navigate in space? Let's say navigate at this point is to learn how to classify paths, right? So if I pass on to the task that I just announced, how to interpret spatial learning task, I can say, okay, maybe one way of interpreting what is happening is to think as following, like a physical path before, okay, I'm kind of repeating myself, the physical path was represented by a sequence of these sigmas, which represent hippocampal cell assemblies, sequence of locations. Now, if I would like to know how I'm orienting, then each location now acquires a direction. You can think of it as kind of a discrete direction vector associated with every location. So like a discrete tangent vector, if you will, at every point, represented by a combination of head direction cells. These ethers are head direction cells. So instead of having a path that was described by a sequence of sigmas locations, now I have a new concept, oriented paths, which are sequence of locations and directions, location, direction, every point, right? These vectors. It's like tangent vectors at every point. From the point of view of, people who are familiar with dynamical systems, for example, approach is a very natural thing, only discretized. It's like discrete location, discrete vectors at every point. So one way of thinking how to interpret orientation, learning orientations in space is basically to say would want to classify these oriented paths, just the same way as we classified simple paths before. And now, classifying paths, what does it mean? Like to classify paths, basically we move them around in a particular space and discover which one is equivalent to which other one, and which ones are not equivalent. So if we would like to do it here, then which topology, which space we want to describe, where these paths are living. Now we can say that since place cells and place cell activity is pretty much independent from head direction activity, there are two independent networks that are producing these activities. We're essentially are talking about some kind of a product between space where this activity lives and space in which this activity lives. And mathematically, this is a very common type of spaces that are called fiber bundles. Essentially, here's one example of such space. You have a base of the bundle. Every point in the base is associated with, in this case, with an interval. Or here's another example. A base is the interval and the fiber is a circle. Every point in the base is associated with the cycle. So this is the kind of construction I'm talking about here. Here's another example of that. Base is a circle and the fiber is a circle. Every point in the base is associated with the fiber. So there are more complex examples, but I'm not going to talk about those. So the net space that we're trying to compute is some kind of a product of representing space for locations times representing space for directions, something of this nature. And simplicial complexes, we can, before we build those simplexes and simplicial complexes as discretizations of these spaces. And now we basically need a discretization of this big space, which is kind of natural, easy thing to do. Like before we used simplexes comprised of place cells separately, head direction cells separately, and now it's a combination of both, right? And we're going to build a large simplicial complex. And by the way, as a comment, I talked about the product of base times fiber. The fiber here is space of direction. It's indeed a circle. So we are talking about a space which is kind of a product, cycle times this base. So it's kind of like a torus, but slightly more complicated. So essentially, our goal is to learn how to orient in space. But I just want to continue the logic of previous computations. We're going to say, okay, can we learn this bundle, the structure of this fiber bundle? And turns out it's not terribly difficult to do. As I said, we look at combinations of place cells, combined activity of place and head direction cells. These are simplexes that discretize this fiber bundle. It can be shown that activity of these cells are mapping. And by the way, as a comment, I discovered recently that this combination, these simplexes in robotics are called, they have a name, they're called a pose, which kind of was surprising to me. So these poses, they can be projected into this combined representing space. They also correspond to regions. If you remember that question I asked, how we interpret neural activity, we map them into space. This time we map them into combined fiber bundle space, and the same thing works, and we can actually carry out our wonderful computation as before and look at what these topological loops do, like how many pieces we have in our system, how many holes we have in our system. We know here I actually did a simplified computation. I modeled rat's movement on an annulus. So we replaced that two-dimensional space with an actual annulus, and the fibers, of course, one-dimensional circles. So we actually have a torus. And when we do this computation, we see that torus actually does emerge. We have one piece, right? And we have two loops appearing. So now it seems like we have carried out the topological line of analysis, and we have our answer. And well, question is, are we satisfied with what we have? And the answer is no. Because as I mentioned before, our previous computations, actually, of course, we cannot pretend that they were precise, but at least we're getting correct time scale. And here I'm saying we're trying to model how the animal is running around this small annulus, and the answer that we're getting is 80 minutes to learn that this is, he's running in probing basically a toric manifold. This is a problem. It doesn't really make sense. And the question is, okay, where this problem might actually come from? Because I'm talking about this topological model and topological approach. Well, it's not much of a model, really, is it? Because all we're saying is that place fields are, in case of hippocampus, for example, place fields are covering our environment, and they overlap, and we're looking at simplexes. And then what comes after that, all this topological analysis, is simply a topological accounting. It's not a really very profound model. We simply count pieces, individual local pieces of information, and we basically estimate how long it takes to build a global picture out of it. So it's a not terribly profound idea, but it's very direct. It corresponds to our conservative approach in neuroscience. People would say that place cells fire in response to place fields, kind of empirical approach. But then we take this logic and put it into this kind of a model, and we get a nonsensical result. And basically, question is why topological approach is actually failing, because the philosophy, something is wrong with philosophy. And question is, what can be wrong with topological approach is too slow because what? And it looks like because it's too empirical. And basically, we're driven to conclude that the system needs to generate information from within. Purely empirical collection of data, like gathering data, like flowers on a meadow. That's an oversimplified picture, and we're arriving to this conclusion based on purely mathematical analysis. The system has to generate information from within to produce meaningful, for us to produce a meaningful model of how the whole process can take place. So we need to rethink orientation learning somehow. So instead of looking at this picture, we can say, okay, given that we have, again, going back, we have locations and we have directions. How can we interpret what does it mean to learn orientation? And what I propose, the way to think about this, second way of thinking about this, we'll say, okay, if we know how to, we have this compass in our hand, we can establish directions, we can, for example, establish alignments. We can find out which directions are, directed in a particular way. And what we're learning these objects, learning alignments. This is a different way of thinking about what is happening, sets of collinear locations. But when we think about this, to learn orientations as identifying collinear locations, now it's an important, conceptually important step, because we're not doing topology anymore. Collinearity and all these terms are coming from geometry. We're basically forced to build a geometry in cognitive map, because topology is basically, obviously not enough. And only then we'll be able to identify things as parallel lines and overlapping or whatever. This language requires geometrical approach. So we need to define geometry via spikes. Now, what we have thus far, I used these oriented paths that consisted of locations and directions of every location. Now, if I would like to define a line, how can I do that? Well, actually, it's not terribly difficult starting from this object. Obviously, what is a line? Here, oriented path is a sequence of locations and directions can be arbitrary, but of course, I expect them to move, to change kind of continuously or contiguously from point to point. But if I fix my direction, every single oriented position has to have the same orientation. Sigmas oriented in the same way. That would be a line. So aligned locations or aligned alignments are oriented paths that are directed by the same head direction assembly. Simple as that. So, and here I would like to introduce a very convenient notation for alignments, just a series of sigmas, these hippocampal cell assemblies, whichever ones we go over, and eta is fixed. Basically, we're moving over position, 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 but the head direction cell is the same. We're guided by the same head direction activity. Now, I can use this language to define a bunch of geometrical notions. For example, two lines or alignments like this in neuroscience way, kind of. They overlap if what? If they share locations. So basically, one of these sigmas has to be the same here and here, and they overlap. Two lines are parallel if they're guided by the same eta. The sigmas can be different. The series of sigmas here, series of sigmas here are different, but the eta has to be the same. Then they should be parallel. I can also introduce concept like dual concept. Here I had a bunch of sigmas and fixed eta. And now imagine if I do opposite, if I have a sequence of eta simplexes that ignite at the same fixed location, fixed sigma and change eta simplexes, that would correspond to a turn, right? It's turns yaw from, moving, sweeping over directions and keeping the same. So I can introduce a bunch of this kind of geometrical notions, but in principle, I should say, we're doing the same thing as before. We still are sitting in this kind of fiber bundle kind of reality. It's locations times directions at every point. Simply, we're pursuing a different task. We're trying to identify a particular structure within fiber bundle. We're trying to identify those straight lines, how they intersect, how, which ones are parallel and so on. Now, and basically we're trying to build the geometry, as I said. Now, next line of, next series of question comes, okay, does this set of relationships define a geometry, right? Or even more, when does a set of relationships define a geometry? Now, in mathematics, this question is answered by establishing universal rules for building a particular geometry, which we call axioms. So we just announce that certain rules are valid for a particular geometry. And since I'm talking about affine geometry here, which was introduced by Euler at the beginning, of course, because he discovered everything, and then Möbius, the same Möbius who created his Möbius strip, and Ferris-Klein and others. So they basically said that in order to define affine geometry, we need to establish three rules, three axioms. One is that, if you have two locations, X and Y, there should be a unique line passing through X and Y. Then for every line, there should be a point outside of it, like this. And once you have a point, there should be a unique line that passes through that point parallel to the line you started from. And the claim is that, if you have these rules, then you immediately have geometry, and geometry is going to be, it's a way to create a consistent framework for logical reasoning, for geometrical reasoning. But now, this is not good enough for our purposes, because when we talk about a plane implemented in terms of neuronal activity, what are these axioms fundamentally in mathematics? They're just proclamations, they're just announcements. We just say that, there is a line passing through every point, there are slogans essentially, right? But when you talk about, we could say the same thing in neuronal terms. We could say a unique alignment passes through any pair of hippocampally encoded locations. We can say that there should be a hippocampally encoded location outside of a given alignment. And we can also say that, a given alignment should be there should be a line passing through this extra point parallel. We could translate these statements into kind of neuronal terms. But that translation is not enough, because what we are interested in, we would like to know that these properties are actually implementable in the system. They should be implementable, physically implementable, physiological. It should be computable. We cannot just proclaim that these statements are correct, like in mathematics people do. We have to actually show that something like this has a chance to be implemented biologically, which is, very different kind of a task. And I should say that, okay, as a starting point, I should say that no matter how neuronal affine plane, no matter how it's implemented, one thing we can say from the very beginning, that this representation has to be discrete or finite. Usual normal geometries, of course, are continuous, and where we necessarily have to deal with discrete finite geometries. And these finite geometries are actually pretty rigid constructs. Like here is an example, Fano plane that has 9 points, and these things are lines because they are in correct relationships with points and other lines. So this is an example of discrete geometry. But these objects are actually pretty rigid because, for example, discrete affine planes, they have to have a fixed number of directions. They have to have the fixed number of lines passing through every location in the geometry. They have to have fixed number of points in any line, and there's a bunch of requirements like this, which may or may not be valid neurobiologically. But what's interesting is that some of these requirements, even though they are so rigid, they directly correspond to what we have physiologically. For example, we have to have this fixed number of directions. And of course, we will have fixed number of directions because we have fixed number of head direction cells and head direction assemblies. They will produce only so many directions at every point and not more. And we'll have the same number of lines passing through. It's interesting that neurobiology actually somehow talks to this mathematics. There is some kind of correspondence. But still, there's a question. If we think about, the population of all these head direction cells that we have and place cells and all these networks, how do we know whether we can accommodate this whole thing or not? And there are some arguments to say that it's unlikely that we're literally going to build a finite geometry with that. It's probably too rigid of a task to be solved by a neurobiological system. So we have to somehow soften the problem. And what we can do, what I propose to do, is to use some, more kind of a physical approach, and to say that we don't know how the whole thing is built and how this geometry is going to be constructed globally, right? But we cannot try to build theory kind of locally. For example, instead of saying that a unique alignment passes through any pair of points, we can say it can pass through a pair of adjacent points. So if you have a point and next to it, adjacent, meaning that you start from sigma and you kind of go in another direction, and then you meet this sigma with nothing in between. So they're adjacent in that sense. So if I give you basically what this rule, or this, I'm hesitant to call this axioms. Let's call them rules, geometric rules. So what I'm saying is that if you start from one sigma hippocampal cell assembly, and I give you another sigma, there is a head direction assembly that leads you from here to here. Let's assume that. It's kind of a minor assumption, actually. It's not terribly strong assumption. Now, another one is hippocampus encodes a unique location adjacent to given sigma in any direction eta, meaning if I start from sigma, if I give you here, I gave you sigma and sigma, and I was saying that there exists an eta. Here I'm giving you sigma and eta, right? You start from a point and you move in a particular direction, there will be a sigma that you are going to meet. And the last requirement I would like to impose here is that hippocampus can explicitly represent overlaps between alignments. If we're going to build alignments using these rules, right, the hippocampus has enough means to represent whenever these alignments are overlapping. This is explicitly a sigma that we're going to explicitly represent this overlap. And it actually turns out that you actually use these rules to build longer alignments from these elementary steps. You can build bigger alignments. It actually can show that geometrical properties will be in place. So like parallel alignments will not overlap. We can show it kind of mathematically that now we're doing mathematics. From these rules, we can deduce this. And also we can show that two non-parallel alignments built according to these rules will intersect only once, which also makes sense. It's wonderful that, we kind of get mathematical consistency, but these requirements are more kind of benign, and we can, hope to see them implemented in physiologically. And of course, we'll have these properties that I mentioned before, the fixed number of directions. So this is something we can start from. And we can also, at this point, make one more step and say that these rules, we can think of them, as imperatives, if you will, so that we can say that these rules are not just descriptions, but requirements imposed on the system's dynamics. So in other words, when the animal is learning a cognitive map, the process of building a cognitive map has to be consistent with this rule. So as we build a cognitive map, we should make sure that a unique alignment should pass through every two adjacent locations, that there should be required eta and sigma assemblies. And so these things are requirements that are satisfied in the process of building a cognitive map. Now, to show how this works, how this can help. Let's say you start from a point, and start from some location, then you move to another location, right? And these are basically two adjacent locations, and we have an alignment. As we move, there's some kind of eta is active on the way. Next move, another eta is active, we move to a new point, but now we can build some alignments, in particular these guys, which were not aligned. Now they have to be aligned. We'll put a line through them. Next step, right? Here we have another alignment, and now we begin to generate extra points because we have this alignment and these are not parallel. We have an overlap between them, and we can build more lines and generate more points like this, right? At the next step, we have yet another point. We can build those connections, generate more points, and so forth, right? So you see how this works. So in only a few steps, as you move around, and if you allow yourself to do this kind of procedures, you begin to generate points that will, in a few steps, will cover your entire environment. So now going back to the problem that we were trying to solve from the very beginning, like our rat was running here, we're building the simplicial complexes, and the problem we had was that these complexes, were kind of produced too slowly. We're producing, what is it called? We're producing coactivity complex from hippocampal place cells and head direction complex, and that process would take too much time. But now, if we say that we have this extra tool saying that a unique line should pass through any pair of, let's say, empirically established locations, right? Then we can generate these lines and actually start producing those lines that are going to intersect in whatever ways, and that will produce more points and more simplexes, yes, that will simply complement what we are building as we navigate. But the difference is that these simplexes take a long time to produce, because they appear as at the time scale at which the rat is navigating in our environment, and these guys are appearing instantly. So if we complement this process, the empirical learning process, with this computationally generated simplexes, then of course learning time is going to reduce very significantly. And this is basically what we want. In that way, geometry is going to help us to produce these structures faster. Now, before I go, and this is basically our way of saying that the system generates information from within, it generates it geometrically. Now, before I give you the times how it works, I would like to say that here is a little problem that appears in this process, and that is that we generate these new points kind of blindly. We generate them in the areas. Here is the example of our environment. We generate them in areas where the animal actually never steps. Like, for example, those points may appear inside of this hole, but physically animal has no chance of going there, or they can appear outside of the enclosure, because we generate them geometrically, wherever they appear, they appear. Now, question is how to get rid of this kind of parasite spurious points, because they're spoiling topological structure of the space that we're trying to capture. And one way to deal with this is to allow these sigma assemblies to decay. Now, of course, these sigmas, they represent cell assemblies in the hippocampus, and it is a physiological fact that these cell assemblies have finite lifetimes, they decay. So what we can do is, and yes, we simulated how this works. This is what you're seeing here. These are timelines of the sigma assemblies. Each strike here is when a particular sigma appears, disappears, disappears, and color corresponds to dimensionality of these sigmas. So redder corresponds to higher dimensional sigmas, and you see that the red lines are very short-lived, but lower dimensional, longer lived, and this is kind of natural thing to model. And what we can do is we actually can allow empirically discovered simplexes to have longer lifetimes, right? They decay, they take longer time to decay. And these points that we generate artificially, computationally, they are short-lived. And actually what we can do is we'll look at those simplicial complexes that appear in that way, and we get, it's actually a very complicated beast, because the simplicial complexes, they begin to be very dynamical, flickering. The simplexes appear, disappear, holes and pieces appear, disappear. But it's possible to adjust your parameters in such a way that this appearance and disappearance remains, so your simplexes can have short lifetimes, but overall topology becomes fixed. And in other words, what it means is that overall these points, they may still appear and disappear inside here, but there appears a hole that represents that physical inability of the animal to get into the middle of this hole. And we actually, in that way, can actually recover correct topology. So the upshot of this, by generating these geometrical structures, we ultimately get viable estimates for time scale of biological learning with these lines that generate extra points, and we get back to this 4, 5, 6 minutes, and this is basically our solution to the problem. Basically, with the geometry helps to recover biologically viable lifetimes. I should say, as I quickly mentioned, that this kind of autonomous endogenous dynamics that we simulated here, that we simulated to produce alignments, is also used it's useful topologically, because some time ago we simulated hippocampal network with rapidly decaying cell assemblies. So now we're talking about purely hippocampal networks. Imagine something like this is happening. If time scale of decay is too short, then that produces a very unstable map. So what this is representing are topological errors, like where it's basically counting holes and pieces in a simplicial complex like this. And you see we get something like 70 holes and 50 pieces, which obviously means that our complex can be very unstable if we introduce decaying cell assemblies. But at the same time, if we allow our system to do these replays, which I mentioned in the first few slides, I was showing this replays that the animals produce offline activity. If we simulate, these cell assemblies replay in the hippocampal map and inject them into the system, it turns out that these guys, they reactivate cell assemblies for a short time, but this is enough to reinstate stability of the network. So this, like for example, here we have topological errors, but then if we introduce replays, then topological errors basically tend to disappear. Instead of 70 holes and 50 pieces, you have just a few, which is a big deal. So replays can stabilize topological map inside of the hippocampus. It's a kind of a separate story. But what we're doing in recent analysis, in the last analysis I talked about, we were producing straight lines. These replays are not necessarily straight; they're arbitrary paths, and we're using them to kind of stabilize topological map. But the way we're using them in this new model is to generate information through geometry. So this is kind of offline topic. Now, I would like to summarize at this point what we've done so far. We used hippocampal and head direction outputs to build kind of a spiking geometry, and that the whole construction was purely intrinsic. We never used external information as we did this, because if you remember my kind of rant about not using place fields are bad, external information is bad, we actually never used this external information to build this. Only the whole thing was built on analysis of simplexes and simplicial sequences, so forth, right? Now, we also saw that topology is kind of more empirical. It's something we have little control over, but geometry is more algorithmic, and it can be used to generate spatial information, kind of guide spatial learning. And also that empirical learning can be kind of complemented by intrinsic learning coming from this geometry analysis. And this actually goes back to this whole line of argument goes back to this long-standing question about the role that is played by geometry in our cognition, by the origins of geometrical perceptions, foundations of geometry, and all that. We're kind of getting back to this question again. Can it be that geometric algorithms are kind of hardwired into our brain? We kind of are almost forced to conclude that. And to set up kind of a stage for the following discussion, I would like to bring a quote from Poincaré from 1896. He's writing, he's basically offers a model of how we interact with the outside world, and he says, let us imagine innumerable telegraph wires, some centripetal and others centrifugal. And the centripetal wires warn us of what occurs outside, and centrifugal wires transmit our response. So he's imagining kind of, wires coming in and out of a telegraph station, something like this. It's late 19th century Paris. And then it says that when a wire is traversed by a current, it acts on a central exchange, this central exchange distribution board. And then he says that it's this complex system of association, this distribution board is our whole geometry. That's his perspective of where geometry is coming from. So this characteristic properties of space are only property of the distribution board. And these are quotations from his book, I believe, Science and Method, if I'm not mistaken. And then he goes as far as saying that different distribution board would be enough to endow space with fourth dimension. So he literally thinks that geometry as a, epiphenomenon produced of neuronal activity. And what I actually find interesting is that this was done in 1896, the same time when Ramon y Cajal was drawing his neurons, which is, I think, is kind of amazing. So how deeply Poincaré was thinking about origins of geometry. And at the same time, about the same time, another geometer, another mathematician was kind of studying origins of geometry, and end of 19th century, beginning of 20th century, gave a complete system of axioms for Euclidean geometry and fine geometry and other geometries. And he was saying that it is obvious, a quote from Hilbert, that every theory is only a schema of necessary relations, and that the basic elements can be thought of in any way one likes. So if, speaking of my points, he says, I think of love, law, and chimney, arbitrary things, and keep relationship between them as between my points, right? Then my propositions, such as Pythagoras' theorem, are also valid for these things. So essentially, here's another quote, maybe even better known in this direction. He's saying that it must be possible to substitute point, line, and plane in geometrical axioms with table, chair, and beer mug. So what he's basically trying to say is that, according to Hilbert, geometry is fundamentally a relational concept. It's a relational framework. So relationships are primary, and the nature of the objects that they apply to are irrelevant. It's a kind of a big idea, I think, and in the context. And he says explicitly that these objects can be taken any way one likes. Substitute point, line, and plane with table, chair, beer mug, right? And given the kind of questions that we are asking, I would say that we would like to replace beer mugs with spikes and spike trains. Now think about that. If we keep relationship between these objects as between points, lines, and so forth, right? We build geometry. We basically synthesize geometry from spikes. So I would argue at this point that this is our attempt to answer how that miracle that we mentioned at the very beginning, how this miracle comes about. So the miracle is, it may be one way of answering what is happening, is that the space, as we know it perceptually, cognitively, it emerges from relational order of neuronal activity. So going back to the problem that we started from, right? Previously, I was discussing how to use geometric relationships to kind of accelerate spatial learning and so forth. And I should say that originally, especially we started from this topological approach. And if you remember the way I was asking these two questions, that we fundamentally would like to know answer to, how neurons encode spatial entities as opposed to how neurons respond to spatial entities. And at the beginning, the entire story was definitely coming in the vein of the second way of asking questions. Neurons were responding to spatial entities, like neurons responding to place fields, and then we build this fiber bundle. And also we're saying that neurons respond to regions. So we're kind of playing safe. It's simply playing safe. But as we developed this model, something interesting happened, because in the process of building this model, we made a very interesting step. How exactly did we build our alignments? These alignments were just, a series of sigma assemblies, hippocampal cell assemblies that are firing in some order. And as they're firing, there's some kind of a head direction assembly that keeps firing in the process. And we're saying that this is our alignment. this construction has makes no reference to any kind of place fields or anything like this. So I would like to argue that this is an example of this beer mug philosophy. We're actually building a geometrical entity entirely in self-contained terms, intrinsically. And what it means that, from the point of view of this miracle, there's not, this miracle kind of disappears. There's not so much miracle anymore. Right. So basically this approach allows us to build elements of geometry related to external world. Yes, because we know that there's this relationship, but also we can actually interpret intrinsically where these lines and geometry is coming from. Now, this was about geometry, and I would like to go back to hippocampus quickly, and we talked about the hippocampus activity is represented by what is it called? Simplicial complex, and every simplex represents a location, right? And actually, it can be shown that the way these simplexes are sitting inside of simplicial complex, it by itself defines a synthetic topology. We can define topology of hippocampal representation again intrinsically, without any kind of reference to place fields and so forth. And now defining topology intrinsically as a kind, what does it require essentially? What are the constituent points? We need to define what are our elementary locations, right? And what is close to what? And the standard mathematical way of doing that is to introduce vicinities. So like this vicinity, like these points which are inside this vicinity are close to each other. These points are close to. This is kind of introduces context of what's close, what's far. And I should say that online, I've noticed there was a series of lectures by, I believe Eisenberg is last name of the mathematician who gave lectures at this mathematical school at Ratmino. There's a series of lectures at mathematical summer school in Dubna, and he gives a nice series of lectures about finite topological spaces, and this is what this is about. We can actually look at those lectures as a complement to this. So if we think of a specific simplex sitting somewhere in simplicial complex, all we need to do is look at the simplexes that surround it, roughly speaking. So this what defines a vicinity. And it can be shown that so defined vicinities are consistent with standard topological definitions, and together they form a very legitimate topological space. And the space was introduced in 30s by Alexandrov. He called them discrete spaces, and this can be thought of as constructive model of, on the one hand, this is topological map, but we actually can make this transition and talk about models of space, which we can think of it as a model of space in which the animal is navigated, kind of cognitive model of that space in which animals navigated, or we can take it further and think of it in more general terms as memory space. It was advocated by Howard Eichenbaum, who died a few years ago, but he was talking about this memory space in which which allows basically to conceptualize reasoning, spatial orientation, in kind of general reasoning in abstract terms. We can relate it to navigation, think of it in navigational terms. So this concept of memory space nicely fits this, this Alexandrov space is a nice model for that space. And it can be shown that, for example, many natural things, like as you move, for example, in your environment, that corresponds to a path in that Alexandrov space. So, and when you move here continuously, you move there continuously. So, trajectories, these simplicial trajectories that I talked about before at the very beginning, they correspond to naturally to path in this Alexandrov space, and the whole thing actually works quite nicely. And the same way, this is, basically I'm repeating myself, that simplicial path is a path in navigational space, and this we can even show a simulation of this. Here's when you move in the environment, these are groups of cells are being active, and that corresponds to combinations of points that you cross when you move in this Alexandrov space. Actually, this object is computable numerically. I can show that moving here this is how you move in that model of cognitive space. So think of this as moving in simulated rat's mind, if you will. So Now, the discrete paths with orientations, we remember that we are talking about this, our object that we introduced, these oriented paths, they actually also exist in this. They can be translated into paths in Alexander space just as well. And we can introduce, those alignments in this cognitive space. And that will basically be a model, a current model of what is the structure of this cognitive space. It includes topology and geometry at the same time, right? So going back to these questions about how neurons encode spatial entities or respond, we can at this point basically somewhat, get rid of that miracle thing and actually get rid of the second way of asking question, ask them more directly, that neurons encode spatial entities, and we can say how synthetically they produce, those spatial entities, topologically and geometrically. And I would like one more quote from Poincaré in conclusion I would like to bring. It's kind of interesting. He says that it's often said that the images we form of external objects are localized in space. It is also said that this space, serving as a framework prepared for our sensations and representations, is identical with the space of geometries. And so to all clear-headed men, this statement, this coincidence might appear extraordinary indeed. This is quite a coincidence. Why, space as we know it coincides with the space as we, produce in our brains. So the answer, how brain represents space, a possible answer is it builds that space from within. And this idea, actually, it appeared before from many researchers, and Ernst Mach has a whole book about this. But what I'm trying to say is that maybe the time has come to kind of revisit these ideas of Poincaré and Mach, because now we kind of have means to do that. And this is it.